Recording perfect. And this is, welcome back to everybody. This is our lecture 23 in high dimensional probability and applications to data science. And last class, we studied PCA, principal component analysis, then the mathematical foundations of it. The basic question there was, how do we visualize high dimensional data, high dimensional distribution, a high dimensional distribution? For example, let's say a genome, the sequence of genes, a human genome, yeah, of a person, so human genome. Let's say you record for every person in the world, you record some part of the genome, maybe a couple thousand of genes, gene expressions. And then you try to visualize it in 2 dimensions, 3 dimensions. In probability theory language, this is what we do. We look at the random vector. We think of the human genome as a random vector. So X is in RD. So for example, X would be the genome, the D genes of a random person, just from the population, the entire population. So imagine this experiment with you're just drawing some person from the world, from 7 billion people, maybe, and look at the genome. There'll be a random vector in RD. For simplicity, we assume that expected value is 0. Otherwise, we just shift the vector, subtract the expectation if needed. And then the covariance matrix, which is a high dimensional version of the notion of variance for a random vector, is, well, what's a variance? It's like expected value of x squared, right? Because the mean is already 0, so I'll not subtract it. So expected value of x squared. In the matrix form, this is now matrices, so it's expected value of x transpose. So that's the proxy of the square. And that's what we call sigma. Let's say call it sigma. It's a d by d symmetric matrix. And we use that matrix to visualize the genome, to visualize the high dimensional distribution. How? We compute the eigenvectors, eigenvalues, eigenvectors. The let's say top, I don't know, let's say top 2, because I want to put it in dimension 2. Top 2 eigenvectors of sigma, and by top, I mean those corresponding to the largest eigenvalues, the biggest 2. They are called principal components of the data of X. And the PCA, the principal component analysis, is the simplest, super simple algorithm where just compute these 2 eigenvectors and then reduce the dimension of the data from RD, from D dimension to R2, from 2 dimensions, by projecting it. Projecting X onto the plane spanned by the 2 principal components, by the span, let's say, how do we call this? Span VI, V1, V2, sorry, V1 and V2. And these are the top 2 eigenvectors, 1, 2. And we've seen these beautiful pictures. We saw them last time too, where we have this data and it kind of nicely clusters, hopefully, maybe not, but hopefully nicely clusters when it is projected onto the span of V1 and V2. Why do we do this? Is because by projecting onto V1, so the direction of V1 is the direction in which the distribution is the longest, is the most spread. And so it makes sense to project there first, because that direction explains most of the variability in the data. Most of the variation will be explained by just projecting onto V1, that the V1 is the best in that case. And if that is not sufficient, of course, you project on V2. Again, V2 would be among all the remaining directions, among all the directions that are orthogonal to V1, V2 now is the best. That direction is explaining most of the remaining variability of the data. And then you can project also onto V3 and so on and so forth. So that's PCA. Perfect. So now there is a big, okay, questions about this procedure, because we're now moving forward. That was last class and we're ready to go forward. Any questions? Cool. So, okay. So now we have a big problem that's kind of lurking in the background, and it's still a big problem. Namely, this procedure, if we want to visualize the human genome, the genome of the human population in the world, this procedure assumes that we have access to the entire world's population. And we don't. We usually have access only to a very small sample of it. Is that enough? How much sample do we need in order to run this procedure meaningfully? So let me write this down. So PCA assumes that we can compute this matrix, the covariance matrix of the data, which is called the population covariance matrix. The covariance matrix of X. Let me rewrite it again. Expected value of X, X transpose. Here, the expected value is effectively the average we computed by averaging over the entire population. In this example, it was world's population. But we can't do that. We don't have the data about the entire world's population. We have a finite sample. Instead of the world's data, instead of all of that, all of the people in the world, we have just a sample that's available for our study, a finite sample. Let's say we draw just N people, not like 7 billion, but just N people for our study. And in the probability language, it means that we're drawing N independent and identically distributed, or let me just say independent copies of X. Is this terminology clear? Right? Independent copies means that these are random variables that are distributed like X, but they are independent random variables. So because we're just drawing N people independently. Perfect. And then we hope, and then what do? We average over the sample naturally, right? We can't average over the entire population. All we have is a sample, so let's average over the sample. So we average over this sample. And we get, so how do we average? Just take the arithmetic mean like that. Xi transpose. Yeah, take arithmetic mean. And that thing is called the sample covariance matrix. As opposed to the population covariance matrix. And then we hope. that the PCA will be okay. That PCA, if we run the PCA, this procedure with these eigenvectors on the sample, I'll just put it this way. I hope it's clear what it is. PCA with input, which is on the sample, the output of that will be approximately the same as the PCA on the population, which we can't compute. which means that the eigenvalues will be about the same, because we need to know which one are the top ones. So we need to know the eigenvalues, and the eigenvectors will also be approximately the same. Vi of sigma. Okay, not a big surprise to you, right? This is a statistics, basic statistics, right? You don't have access to the entire population. You take the sample, you look at how much the sample is, and so on and so forth. So at this point, it looks kind of boring because you've studied this. Of course, you do the sample, right? You're statisticians, some of you, but this is actually coming to the point where it's actually not very boring. It's actually very delicate question. How large, at this point, how large should the sample be in terms of D? So is it, let's say, how many people do we have to include in the study? Is it like linear, maybe? Or maybe we have to include exponentially many people? Think about it like this. We have the genome. It's very complex, right? The genome is it determines our individual features. If we want to capture the complexity of the genome, how many people do we have to sequence? It's a very natural question. It's not even a statistical question. It's a kind of a question that's related to the complexity of the genome. Do we have to? Is it okay if we let's say include as many people as the number of genes that we have, like 5,000, for example, of that order, linear? Can we do it with smaller number? Probably not, right?
Isn't it actually dependent on the inherent complexity of the genome? For example, if it's inherently one-dimensional, then it will be a completely different number than if it's very, very complex.
Yeah, exactly. That's actually a great question. So who knows, right? So maybe the genome, just in our mind, let's say, what if the genome is just a replication of one gene? So effectively, it looks like high dimensional, but reality is just one dimensional. Then we don't need as much people in the sample. And let's assume at this point, let's assume the worst case scenario, that we don't know anything about the genome and every gene could express its own thing. And let's assume that. But later, that's actually a very great way to reduce the complexities, to think, okay, actually genes cooperate. They're not, each individual thing is its own thing. So maybe the inherent complexity is less, and we will do that too later. But for now, let's assume that the worst case scenario, we're still in the exploratory data analysis situation where, imagine we just have this data, we just have this huge table of genes, and then what? We don't know anything about the data yet. So the question is, suppose the genome is super complex, every gene is its own thing, and how many people do we need in order to capture that complexity of the genome, to visualize it properly? Do we need linearly many in the number of genes? Do we need exponentially many in the number of genes? Could be, right? Because we've studied the curse of high dimensionality. It sometimes could manifest itself. Sometimes, maybe that's one of the cases where you can't go with linear, and that becomes the problem that's called covariance estimation problem. That was very popular. It's very popular nowadays. Covariance estimation problem. Basically, is to decide which is which, right? To decide how big sample it is and how well we could estimate the covariance. And what if we don't have all that sample, and so on and so forth. So that's the source of very interesting questions. And fortunately, this is the truth. So we only need linearly many even if the worst case complexity of the genome or the problem, we only need the sample of linear size in the dimension. It's kind of intuitively should be clear why we can't get less. For example, we can't hope that we can have just logarithmic in the dimension. Just take very, very few people and hope to capture the entire complexity of the genome. That's silly. It doesn't make any sense. And we can easily show that linear is necessary, and we'll also show it is sufficient in the worst case. So our plan for this week would be first to approximate the population covariance matrix by the sample covariance matrix, like this, and then use first order perturbation theory. I'll explain what this means. Use perturbation theory, which basically says that if the two matrices are close to each other, then their eigenvalues are close to each other, and the eigenvectors are close to each other. To conclude this. To conclude that the eigenvalues and eigenvectors are close. Okay. With linear sample. That's what we. Okay. Is the plan clear? Yeah, very good. Cool. And this is why we introduced matrix norms, because we can only ask this question in some norm. We approximate the sample, the one matrix by another matrix. But what do we mean by approximate? How do we even know that these matrices are close to itself, to each other? That's where the norm is needed. That's what measures kind of the length, the difference between them. And we will do this in the operator norm. We will do this in the operator norm. Why? Because perturbation theory works for the operator norm. And I'll explain it later. Good. Okay, let's try. Let's try to do this and see if it's easy or not to do. All right. So how do we do this? How do we do one? We need the norm of sigma n minus sigma. And that is the operator norm. The way the operator norm is defined is just this first singular vector of sigma n minus sigma. Singular value, excuse me. The first singular value, the top singular value, the maximum one. Now, if you recall, the singular values are, what is this? They're the eigenvalues. Let's say singular values of A. They're eigenvalues of A transpose A. And then you take the square root. But these matrices are symmetric. So A transpose A. So it'll be A squared. Okay. And then they take the square root. So basically, we'd have the absolute value of the eigenvalue. So this is the same as maximum of the first eigenvalue of lambda n minus lambda. Not maximum, just the first eigenvalue. And we can compute the eigenvalue, the top eigenvalue, by maximizing the quadratic form. Maximizing the quadratic form, the canonical standard quadratic form V transpose matrix V over all unit vectors V. S to the d minus 1, just to note the sphere, the Euclidean sphere, unit sphere in dimension d. So the set of all unit vectors. I have to include the absolute value around. Okay, that's what we did last class or the class before, and we will also do a part of this in the homework. So this is justified by the homework. We do part of the class in the homework. Okay, so the point is the operator norm is computed by maximizing this quadratic form. Perfect. What is this? Let's see. That'll be fun. V transpose sigma n minus v. What is this? V transpose sigma v. What's sigma? Sigma is expected value of xx transpose. Okay, times v. Let's compute. Expected value is linear, so I'm taking it out. V transpose x, x transpose v. And I'm grouping them as this. And this R, let's see, there's both of these factors are the inner products, Vx, and by definition, and this is xv. And so we get expected value of xv squared. Yep. And the second term, this is one of the terms. The second term is with sigma n, but we can guess what it is. V transpose sigma n v. Okay, let's just think instead of trying to compute this. If I take the quadratic form with sigma, I get this expectation of that. Now just imagine if I take the quadratic form with sigma n, and how is sigma n different? Instead of the expected value of the entire population, it takes expected value kind of over the sample. So what will be the difference on the right-hand side? This. Instead of the expected value over the entire population, I'll just have the expected value of the sample. You can verify it formally, but clearly, this is what we should expect to happen. And that's true. Check. Okay. Okay, let's keep going. So this is, and we're continuing computing the operator norm here. So this is a maximum over all unit vectors of, okay, of what? Of, I subtract this from this. Okay, let's think. This is one number, so maybe I'll put it inside. So let's something like this. Actually, I think it's this. Xiv squared minus expected value. Xv squared, yes. Good. Okay, some boring computation, but here it is. Now this is a little mess. Let's just think, what is this? This is kind of it's a random variable, first of all, right? It depends on the sample, of course, and the sample is taken at random. Some random variable. This random variable depends on v. So let's call this z of v. It's random variable whose distribution depends on v. Not distribution, sorry, but whose value depends on v. And then we're taking the maximum. This is interesting. So we have a collection of random variables, z of v, indexed by v. And we take the maximum of that. What do we call even that? Do you know? This is like we have, what is a probability concept for a collection of random variables that depends on some parameter. And this parameter, by the way, is a continuum. It's not like 10 random variables, but it kind of slides. Z of v, and v is a kind of a continuous parameter. What if v was time? What do we call a collection of random variables that are indexed by time?
Random process?
Random process, exactly, or stochastic process. Yeah. So this is a random process or a stochastic process. indexed by points in the unit sphere. Okay, this is a little mind-blowing because we don't usually index process by points in the unit sphere. We index them by time. And even if we index processes by time, then what is the canonical process? What is the most familiar random process that you know?
Brownian motion.
Brownian motion, yes. A totally random process, right? So let's compare this to something that we at least have a better idea of, to the Brownian motion, which is kind of an exemplary stochastic process. Is called also known as Wiener process, more formally, which is indexed by time, b of t, from 0 to infinity. And it's indexed by time. Okay, have you heard Brownian motion as a mathematical concept? It's an infinitesimal limit of a random walk, of a simple random walk. Like I stand here, and I can step right or left with probability 1/2 each. So at every point in time, I flip a coin, and if it comes up heads, I go right. If it comes up tails, I step left. And then I'm performing this at every time moment. I have this random walk in discrete time. If I can flip coins every second, that's a discrete version. And if I can flip it at every millisecond, I'm doing a more refined walk. And the limit of that, when I flipping coins every point in time, every moment in time, that's called Brownian motion. It actually exists. This limit exists. And the path of the Brownian motion look like this. Let me show you this. Something like this. Someone generated 1, 2, 3, 4, 5 instances of a Brownian motion, 5 independent paths of the Brownian motion. It looks like this. And it is one of the Brownian motion is a process that's most important in financial applications, for example, modeling stock prices and modeling anything else, any kind of very disordered random process can be modeled as random motion or its variance. So this is something that at least we can think about as a random process. But now we have something else. We have this random process z of v, and we take its maximum. Let's just do this metaphor. Let's think about what's the Brownian motion would look like, the maximum of the Brownian motion. So max, taking the maximum of the Brownian motion, just in the same way as we have to take that one. Let's say up to capital T, up to time capital T. Let's test our intuition. What do you guys think? Here's our Brownian motion, and we fixed some time horizon. In this case, it was maybe three days. So we let the stocks run for 3 days, and we're asking what is the maximum. So at this point, the maximum was attained, and it was about 2.9 or something for this process, and it is like 1.5 maybe 1.4 for this process, minus 2.5 for this process. So what is the maximum? The maximum of the Brownian motion, time less than t. Let's just get rid of the absolute value first. As a function of t. Should it be like linear, logarithmic, exponential in t? What would be your intuition about this? Let me think about yours. Yeah. Evgeny, you're right. Okay. Think about yourself. You're just moving. Just think you go right or you go left. And you repeat. And then after t days, where are you? How far did you deviate? That's a question of the standard deviation, right? So after t days, how much do you deviate? Well, you do this plus or minus once, random variables. The standard deviation of the sum of the random variables is what? Is a square root. Standard deviation is a square root of the variance. The variance adds, so it's t, square root of t after t days. This is just a heuristic. It doesn't show that here we're talking about the maximum deviation, not at the given time, but that's okay. It's still actually it is very close to the truth. It's square root of t. Square root of t. Root of t. If you ever have a course in Brownian motion, that's what you'll learn. One of the biggest problems in Brownian motion. And the same question we ask now about a more general random process that's indexed by, I don't know, indexed by d minus 1 dimensional time. Can there be time that's 2-dimensional even? I don't know. Something like this. Is our time 2-dimensional or 1-dimensional? How do we know? We live in this thing. Anyway, so this is a question. We have a stochastic process that's more no, I'll not say more general than Brownian motion because it has a specific form, but it's indexed by the sphere. And we want to do that. All right. The difficulty in this question lies in the fact that the sphere is too large. The sphere has too many points, infinitely many points. In fact, a continuum many points. If it had only 10 points, just imagine the sphere had 10 points. Then we would do the union bound. We would control each z of v separately. And that is easy. This is, what is z of v? For fixed v, it's a sum of independent random variables. All right, we'll do some Bernstein or Chernoff or something like that. The sum of independent random variables. We could do it for fixed v. The problem is that then we would have to take the union bound. And the sphere is not 10 points. So we'll not just add these 10 probabilities together, but the sphere is exponentially large. So that is the problem. The solution for this, we already know the solution for this, as we usually discretize. The sphere is continuum, but let's replace it by something finite. After that, there is finite. We could take the union bound of a finite set. And that is the content of our next step in this process, next step of the solution. It's called the epsilon-net method. It's very general. Everything, by the way, that we're discussing now, it's much more general than problem of genomes or covariance. So you'll have this, after this course, you'll have the soft skills, not only just to solve these problems. Anyway, so the epsilon-net method. This is what we would like to do. We would like to replace the sphere, the unit sphere, by a discrete set of points. Just discretize the sphere, something like this. How fine can we do this? How many points do we have? Unfortunately, exponentially many. We actually already kind of showed that at some point, that we need exponentially many points to put a small net on the sphere. That's because the volume is so exponential. That's because curse of high dimensionality. But this time, exponential should not scare us, because our probability bounds on this will also be exponentially powerful. They will fight each other. Bernstein is exponentially powerful. Chernoff is exponentially powerful. Höfding is exponentially powerful. All this, remember this probability is like e to the minus something, something, something. So that's fine. They will be able to fight the exponentially many points. Okay, let's put the epsilon-net on the sphere. So we're claiming that for any epsilon, this is a beautiful result. For any epsilon, the unit sphere has an epsilon-net x1 through xn with the number of points that's exponential, something to the power of d, where d is the dimension. and some dependence on epsilon. Formally, what the epsilon-net means here, it means that any point on the sphere can be approximated by epsilon approximated by a point on the net. So there exists, for any point in the sphere, there exists a point on the net, which is epsilon close in the Euclidean norm. Good. Cool. What does it mean geometrically? Well, here is any point, like any point here, any blue point is within epsilon from a red point. Well, but that simply means that the red points, if we put epsilon balls, round balls around each red point, they will cover the entire sphere. So the epsilon balls, the balls of radius epsilon, centered at xi, cover the entire sphere. Is this clear? Yeah, because every point is within epsilon from xi, and that means that the epsilon ball around xi cover that point, and that happens for all. So that's it. It's just a covering. So we're looking at the covering of the sphere with a small number of balls. Good. So how do we do this? Let's do an algorithm. We'll actually find the algorithm to find epsilon nets or small coverings. Algorithm. First step. Choose the first point arbitrarily. Any xi on the sphere. Second step. Choose any point x2 at distance at least epsilon from x1. We want it to cover as much area as possible, right? We don't want the same thing. So at least epsilon. Then choose any point x3 at distance at least epsilon from both of the previously constructed points. And then choose any x4 at distance greater than epsilon from the previously constructed points. And the pattern is clear. You just keep going. And we stop when the step becomes impossible, when there is no way, where we can't find any point that's farther. Okay, so that's an algorithm, and we claim that this actually constructs an epsilon net for the sphere. It's a very interesting proof, very interesting claim, and let's check it. So is the algorithm clear now? Well, any questions before we go on with this?
So we don't need the restrictions at distances less than 2 epsilon. We will show it.
Yeah, just epsilon. Yeah. Yeah, so we claim that this is actually an epsilon net. First, x1 through xn is constructed such way is an epsilon net. Interesting. Is this clear? Suppose not. Let's just think. So suppose it is not an epsilon net. What does that mean? It means there exists a point, a blue point here. The point on the sphere, right here, which cannot be approximated by any point. And that means that it lies farther than epsilon from any point. But if it lies farther than epsilon from any point, we should not have stopped. We should actually included one of these points and kept going. It's just by the stopping criteria of the criterion of the stopping criterion is when you can't find anybody farther, anybody epsilon far from the constructed points. And if you can find anybody, then of course everybody is within epsilon. That's it. So if you just think about the stopping criteria, criterion here, you will see that these points form an epsilon net. Okay, is it okay, clear? Yeah, if it's not clear, just think. I believe like you need 10 seconds to think about this offline and you'll get it. Okay, that's one claim. Second claim, that the epsilon half balls centered at these points are disjoint. So we have one ball, let's say. They cover the entire sphere, and the sphere, let's say the sphere goes this way. They cover the entire sphere. But when we reduce the radius by 2, they become packing. So they become disjoint. Why? Again, let's just think. All these points are epsilon separated, right? So if it happened that this is not true, then it would mean that there are 2 epsilon, this is epsilon over 2 ball, centered in xi, and another epsilon over 2 ball centered in xi. And there will be some point in the intersection. So if not, right? So if they're not disjoint, there will be some point in the intersection. And that means that the distance between that point and xi is less than epsilon over 2. And the distance to another point is also less than epsilon over 2. And by triangle inequality, it means that the distance between the 2 points must be less than epsilon. And that's a contradiction. So all these points are epsilon separated by a construction. Good? Guys, you're with me? Everything is good? Cool. Okay. So by construction, the points are epsilon separated, and because of that, the epsilon over half balls are disjoint. And so the picture now looks like this. Actually, maybe here. The picture looks like this. This is my unit sphere. We have epsilon over 2 balls that are separated. So this one, let me see, sphere, radius 1. These little balls, radius epsilon over 2, and they're separated. And I'm claiming you can't pack too many balls like this. There can be too many balls because of the volume reasons. All of these balls, first of all, they lie inside a slightly larger ball, namely of radius 1 plus epsilon over 2. Yeah.
Yep.
Just want to include everything. So they lie in epsilon over 2. And they're packing. They form the packing of it. So let's compare the volumes. So all epsilon over 2 balls, they lie in the 1 plus epsilon over 2 ball. And so let's compare the volumes. The volume of these little balls is n, how many of them, times the volume of each. And it is less than, because it's a packing, it's less than the volume of 1 plus epsilon over 2 ball. this is because of the packing. So I just took the sum of these red balls and I said it's less than this, the entire ball. Good. Okay, so n, the number of epsilon at n is less than the ratio of these two volumes. I'm just solving this inequality for n. Good, and that's it. We know how the volume scales. Right? You take something, you multiply it by, let's say, by 3. So you increase, multiply by 3, and then dimension d, the volume multiplies by 3 to the d. Yeah. And so, and here we multiply by 1 plus epsilon over 2. And so it scales like this. And here we multiply the unit ball by epsilon over 2. So it scales like this. And we're done. This is epsilon over 2 plus 1 to the d.
May I ask a question?
Yes, yes, Maxim, go ahead.
Would we get a better like inequality if we say that these balls lie between two actually circles from this 1 plus epsilon over 2 radius and 1 minus epsilon over 2?
Ah, yeah. Beautiful question, yes. Like this, right?
Yeah. Or I guess it would be the same like asymptotic in D, but still.
Yeah. That's a good question. So we will have we would have here, let me see. Yeah, so we would have here minus the volume of B of 1 plus epsilon over minus epsilon over 2, something like this, right? That'll be the volume of that ring. And we have here 1 plus epsilon over 2 to the d minus 1 minus epsilon over 2 to the d, epsilon over 2 to the d. It's a good question, actually. You know what? I think what it can at best get us, and maybe it does. Actually, it's great. Okay, great exercise. I don't see it at this point, but what I think the truth is that here the dimension d should be actually d minus 1. It's a better result. Should be true, and that is because the sphere is not d-dimensional; it's d minus 1 dimensional. And the usual idea is that the covering numbers, the epsilon-nets, they are exponential in the dimension of the manifold. And the dimension of the manifold is d minus 1. And maybe what you're doing here by taking this ring is that would produce the dimension d minus 1 when you try to do the asymptotic analysis of this expression. That's my first guess. Yeah, try to do this. Because the ring is kind of a fattened version of the sphere. So now you're kind of saying, yes, we're actually not only taking the packing of the ball itself, but the sphere. Did I answer your question?
Yeah. That's also interesting that 1 minus epsilon over 2 to the power of d is actually for large d is small, right? So maybe it wouldn't even matter at all.
Yeah. Yeah, but this is such a small difference between the power d and the power d minus 1. So it's only epsilon difference. So maybe that will manifest itself. I think it would actually, because it would cancel. I don't know. Okay, I don't know. It's a cool exercise to do. And regardless of this, even if your idea doesn't hold, it's a nice exercise to show here that the actual power is d minus 1. But again, in like 30 years of doing this, I only needed one occasion on which I actually needed d minus 1. So yeah, perfect. Yeah, thank you for the question. Anything else? Any other questions? Good. Okay, so we did one important thing. We found an epsilon-net, a discretization of the sphere with small number of points. and small exponential, but yeah, that's the truth. In the process of this, we also discovered a very interesting interplay between the covering numbers and the packing numbers. In fact, covering numbers and packing numbers are almost equivalent to each other. The number of balls that are needed to cover a set and the number of balls that are needed to pack inside the manifold disjoint, they're almost the same up to this scaling. So that is, in fact, is part of the proof. That's what we did. In fact, we proved the covering we constructed the covering by constructing the packing. Because the algorithm actually constructs the packing.
But does it somehow indicate that it's an optimal packing? Like we do?
No.
Packing usually.
Yeah. So the non-optimality is in the constant of 2. That's what we lose. That's where we lose between covering and packing. Epsilon covering and epsilon over 2 packing, they're equivalent, but you lose this factor of 2. So if you don't care about what constant you have here, they're equivalent. If you do care, then not, and then it is not an optimal packing, actually. Any other questions? Good. Okay, good. We needed 2 things, actually. One thing, we needed a small net discretization. Now, great. Assume that we discretize the sphere. But how does the norm change? Because remember, what we're actually after is let me see here. Where is it? We wanted to this is a plan. So we want to approximate something that the norms in the operator norm. The operator norm is a supremum over the sphere, fine, but then we're discretizing. So how does that affect the norm? And that is our next step, a non-trivial proposition about how to compute the operator norm on a net. So instead of the sphere, I will be computing on the net. And the proposition is this: if we have any matrix and we have a net epsilon-net, the operator norm, which formally is the maximum, which is a maximum over the unit vectors of AU. That's a definition of the operator norm. We can compute it approximately on the net. So I'm just replacing the sphere by the net here and do nothing else. And I'm losing a little factor. Epsilon is small, so it's going to be close. So instead of the sphere, I'm picking a net. And I'm saying that that's fine. Taking the supremum over that net will be approximately the same. Okay. Is it believable? Yeah, guys. Yeah, the smaller epsilon, the finer is the approximation, fine. This is actually a non-trivial lemma, non-trivial proof. Why? It's believable, I agree. The problem is that the operator can really be ugly. It could take one direction. We don't control anything. It's any arbitrary operator, any metrics. And the metrics can be ugly. There may be just, let's say, one direction in which the metrics just stretches this 1,000,000 times. And that direction, maybe it just falls just tiny bit between the points of the epsilon net, and the net does not capture it. You know what I mean? That does not happen. And that's why actually the lemma is a little bit non-trivial. So proof, and you guys follow this because the homework actually is, one of the homework problems is very similar. So the proof is very canonical. First, you choose the optimizer of the original problem. So there exists U. So you choose a solution regional problem for which AU attains the operator norm. Okay. Second, we approximate that U by a net. So there exists X on the net for which X minus U is less than epsilon. This is by definition of the epsilon-net. So far, so good? Okay. And third, now we try to bound the difference between AX and AU. Between AX and AU. Okay, let's do it. This A applied to X minus U by linearity. Then we use the operator norm. Just like this. This is definition of operator norm. If we, so remember this, right? So by the definition of operator norm, the norm of A y is less than the norm of A times the norm of y. And that's because the norm of A was defined as by maximizing the AY over the norm of y. Okay, so I did this. Okay, and then, and this is less than epsilon. So this is less than A, norm of A times epsilon. Good. So far, so good. Yeah. And fourth, finally, from this, I can conclude that these two are close to each other by triangle inequality. So AX, how do I set up triangle inequality? So it's AU minus AU minus AX, I guess. That's what it is. Which is greater than, now we have triangle inequality, apply triangle inequality, U minus the norm of AU minus AX. The norm of AU is the norm of A, that was the maximizer. And this we bound already. This is the norm of A times epsilon. And we're done. 1 minus epsilon times the norm of A. QED. It's a simple lemma, but it is, I think it's a little less non-trivial than you would think, because if I didn't know the proof, I would say, oh my goodness, maybe there is some very bad direction, like this one, in which the matrix just stretches that direction just between, kind of stretches between the epsilon net points, and the epsilon net actually doesn't capture it, but it doesn't happen. So here we go. So we set up all the ingredients that we need to, most of the ingredients that we need to for the analysis of covariance estimation problem. We found an epsilon net that is reasonably small, right? Exponential, fine. We showed that the operator norm actually can be computed approximately on an epsilon net. And what we'll do next is we'll go back to probability theory, go back to our stochastic process like this. We will replace the sphere with epsilon net, just like we can do that now. The epsilon net is now not as large. It will be exponentially large, but it's okay. And then we will use one of these inequalities. I can't even remember which one, maybe Höbing's inequality, for example, or Bernstein. For each V separately, this is a sum of independent random variables. And so it has a very nice concentration random, exponential. So we'll bound it with exponential confidence, which will be enough to counteract the exponential complexity of the net. So I'll take the union bound of exponentially many events, but the union bound of exponentially small probabilities. They will interlock each other, and that'll be, that's a plan. That's called the epsilon-net method. And then we'll talk about perturbation theory a little bit, first order perturbation theory, and we'll have covariance estimation. Cool. Okay, guys, any questions? No questions. Okay, perfect. Okay, let's see. As promised, every let me actually stop recording now. Yeah.